All right, good morning, e-learners. Today we're going to do 1.5b. As I stated on Friday, sometimes I take 2 days to cover the material. Now today I'm not going to cover any new material. I'm also not going to be going over the homework. If you have any specific questions, email me. What I am going to be doing is giving you a second look at the material. Sometimes we cover so much stuff, I know that we need 2 days to get a really good taste of it. All right, so that's what we're going to do today. All right, your homework tonight, please write it down. You can press pause if you want. So once again, the section is entitled Postulates and Theorems Relating to Points, Lines, and Planes. Remember, we're going to have we're going to have 5 postulates and we're going to have 3 theorems. Remember, we don't prove postulates, but we do prove theorems. So last class, the startup of this was we already had 4 postulates, postulates 1 through 4. Remember, 1 and 3 dealt with a ruler. It's called the ruler postulate. 3 was the protractor postulate. Basically, the setup of how we set up a ruler and how we set up a protractor. The more important ones, postulates 2 and 4, were called the segment addition postulate. The segment's made up of 2 segments. You add the 2 up to get the whole. And the same thing with the protractor. If 2 angles make a larger angle, add the 2 up, and you get the larger angle. That's called the segment addition postulate. That's postulate 3, and postulate 4 is the angle addition postulate. So we have 5 postulates we've got to go over, starting with postulate 5. All right, postulate 5 is the one that has the most stuff to it. It has 3 basic statements. Here's the shortcut method. All right, the 3 basic statements are this. Right, a line has to have at least 2 points, so 2 points for a line. A plane has to have 3 points, and they have to be non-collinear. That means the 3 points don't make a line. And lastly, space has to have at least 4 points, and those 4 points can't be all on the same plane, so non-coplanar. So this is the shortcut method, right, or the shortcut for this postulate. So it's not saying that a line only has 2 points, but it's saying basically 2 points define a line. A plane, 3 non-collinear points define a plane. And lastly, space, right, is made up of at least 4 non-coplanar points. So postulate 5 is the easiest one to wrap our head around. It's also the one that we won't refer to too often in geometry. And remember, we don't. So this why thing, why is this true? Remember, I gave multiple demonstrations. Remember, a line, you can't draw more than 2 lines through 2 points, right? Or sorry, you can't draw more than 1 line through 2 points. With a plane, you need 3 non-coplanar points, non-collinear points. I can't talk today, apparently. And space, you need 4 non-coplanar points. Okay. Moving on to postulate 6. Okay, this is where we really start to get into the meat of things right here. Postulate 6 says through any 2 points there is exactly, not sometimes, sort of, once in a while, but exactly 1 line. Not 0, not sometimes 2 or 3, but only 1. So if I draw 2 points on a piece of paper, right, how many lines can you draw through those 2 points without curving it? Right, there's only 1. Okay. All right, postulate 7, right, extends that same idea to planes, and it says through any 3 points, well, you can have at least 1, but if the 3 points are non-collinear, right, they don't form a line, then only 1 plane. Remember, I gave the demonstration where if you had a rod, a stick, a line, right, you could wrap that with an infinite number of planes, right? Infinite number of planes touches that line. But as soon as we have 3 non-collinear points, right? Think of the vertices of a triangle. As soon as you have 3 non-collinear points, right, then there's only 1 plane or 1 flat surface that can touch all 3 points at the same time. Okay, so if you just have 3 points and it doesn't tell you anything any more descriptive than that, then you can say at least there's 1 plane. But if it tells you that there's 3 non-collinear points, then there's only 1 plane. Boy, these are some test questions right here. Postulate says the following. It says, if 2 points are on a plane, all right, I need a plane. Remember, that's not a true plane right there, but that's how we draw it in 2 dimensions. So if we have a plane and I have 2 points on the plane, then the line that goes through the 2 points is also on the plane. Well, think about this. If it wasn't, right, if it wasn't on the plane, then that line would have to curve up or down, right, above the plane and then come back to B. You couldn't have a straight line that connects A and B if A and B are on the plane, right? You couldn't have a curved line that connects A and B because then that line wouldn't be on it. But if A and B are on the plane, then only one line connects the two, and that line is on the plane. On the plane. We're running through these pretty quickly today. All right, postulate 9 is the easy one. If you have two planes that intersect, well, clearly it looks like a plus symbol, but remember, we're not talking about the tire shape. We're talking about where the two planes intersect. Where they intersect, right in the middle, and they form a line. So if two planes intersect, then that intersection is a line. Now, although I did give some description of why these things are true, I never really proved any of the postulates. We accepted them as true. All theorems will be proven. In fact, we'll do that today. We did two of them on Friday, or the last class. We'll do one of them tonight for homework, the one that we left off. So let's look at those three. All right, theorem 1.1 is an easy one. It simply says, if two lines intersect, right, if two lines intersect, then they only intersect at one point. Okay, we've got to prove that, right? And we're making a claim that if two lines intersect, they can only intersect at one spot. Now, we call this an informal proof because I haven't taught you how to formally do a proof yet. So the statement is made up of an if part, right? If two lines intersect. We call that the given. I will tell you, if two lines intersect, we accept that as being true. It's the then part that we have to prove. So we got to prove that they can only intersect at one point. So let's see if we can do that with the given knowledge that we have so far. Remember, we can use definitions, postulates, and any other theorem. Since this is the first theorem, well, we got no theorems to use. But we can use definitions and postulates. Okay, so it says if two lines intersect. So let me get two lines. Well, they intersect. Well, if they intersect, then we'll just say that they intersect at point A. Okay. If they were to intersect again, well, I would have to curve that blue line back down to the red line, and they would intersect at another point. Well, the reason why this isn't true is because not only does that defy the definition of a line, remember infinite series of points that extend in opposite directions, I curved it back to the blue line. I'm not going in opposite directions now, but it also violates postulate 6. Remember postulate 6 says if you have 2 points, then 2 points, exactly one line goes through them. Well, look, I got A and B, there's 2 points. I have 2 lines that go through them, the red one and the blue one. Well, if we accept postulate 6 as being true, well, then we can't accept that 2 lines can intersect at 2 points. Okay. Theorem 1.2, the one that you'll prove tonight for homework, says this. If you have a line and a point not on that line, right, then there's only one plane that touches both the line and the point. And that's what Theorem 1.2 says. You will prove that tonight for homework. Follow the steps. They kind of guide you through this proof. Well, that only leaves us with one left, and that's Theorem 1.3. We'll prove this one. So Theorem 1.3 says this. All right, it looks like we got our old intersecting lines again. It says if 2 lines intersect, then exactly one plane contains both of those lines. In other words, those 2 lines would lie flat on the plane. Okay? Well, we got to prove that. All right, here's the proof. This is the more complicated proof. So the if part is if 2 lines intersect, and the part we have to prove is that exactly one plane contains the line. So this is pretty slick. All right, so 2 lines intersect, right? We know by one of our postulates that if they intersect at exactly one point, right? Well, it's a line, right? The blue is a line, so therefore, by one of the postulates, we say, and this is postulate 6, that there's got to be a second point on the line. Right? Postulate 6 says that there's at least 2 points that make the line. Well, so therefore there's a point somewhere on the blue line other than A. I'll simply call it B. Okay. Well, I could say the same thing for the red line. There must be another point on it by postulate 6, right? Well, let's take a look at those 3 points. Right? Are they collinear or non-collinear? Well, we know if 2 lines intersect that they can only intersect at one spot, right? That's Theorem 1.1. And then therefore we know that they must be non-collinear because we put B on the blue line, we put C on the red line, and we've already pointed out that the one spot they intersect is point A. Therefore, A, B, and C are non-collinear. We're almost done. One more statement, and we've proved it. Remember, we're trying to prove that the 2 lines intersect. If the 2 lines intersect, then only they lie on one plane. Well, postulate 7 says that if you have 3 non-collinear points, I got 3, 1, 2, 3, A, B, C. They're non-collinear. We proved that. Well, there's only one plane that contains them. Therefore, we proved what we wanted to. If 2 lines intersect, then exactly one plane contains the lines. That's how our proof is done. Okay, so we don't have time today to do the classroom exercises. You can do those on your own if you'd like. The homework tonight is 13 through 20. Please email me if you have any questions on how they're done. I will call out the answers on next class. And then we'll go over, I don't know, test-taking procedures, what tests look like. But just remember, if you had me in the past, all tests look pretty close or pretty similar to the practice test that we'll do tomorrow, next class. And that does it. All right, guys.